Hey there, everybody. Welcome to part 3 of our ongoing trilogy of learning, the final chapter. Today, let's talk about recursion relations. You might be wondering, well, what exactly is a recursion relation? And that's kind of a loaded question, but we can begin with an example, right? Let's say that we have we're given some initial values to a sequence of integers. So let's say a of 0, which is the first index, is equal to 2. A of 1, the second index, is equal to 1. And we want to define our relationship as whatever the current value is equal to the previous two values multiplied against each other. So, given that relationship, what would A of 2 be? Well, it's just the previous two values multiplied. That's 2 times 2, which is 4. What would A of 3 be? Again, the previous two values, 2 times 4, which is 8, and so on and so on. And we could generalize our relationship with A of n. No matter what value we have, A of n, what would the answer be? Well, A of n could be defined as A of n minus 1, the previous value, times A of n minus 2, which is two values behind A of n. And so we could generalize it with this equation for all values n greater than or equal to 2. Right? Because if we were at the first index and we were, A of n minus 1, then we would be giving a negative index, which would be impossible. So we define it like this. And so then we see that a recursion relationship, is some parts a loop, but in many ways it's also a leap of faith, because you have to have faith that eventually your answer is going to turn out just the way you want it to be. A of n is equal to 3 times A of n minus 1. Our initial condition is given as 2. So kind of going from that initial example, we have an initial condition on our sequence timeline. A of 0 is 2, and we are given A of n already. We want to work backwards to try to get to where we can use A of 0 to solve for our recursion relation. So A of n is equal to 3 of A of n minus 1, right? And that is given. We see that 3 of A of n minus 1 only needs A of n minus 1, or only relies on the previous value in our iteration. So then what does A of n minus 1 look like? Well, all we need to do is we see that A of n is included in our formula for A of n, so let's plug A of n back into itself, right? So this A of n minus 1 is going to be replaced with A of n, but every instance of n becomes A of n minus 1. So what does 3an minus 1, replacing all the n's with minus 1s, look like? Looks like this: 3 times A of n minus 2. So that's what we're plugging in to A of n minus 1, this formula here. Then A of n minus 1 is 3 times 3 of A of n minus 2. Everybody see that? This 3 is a remnant from the next value in the iteration, right? Nothing happens to it, so we keep it. So this just simplifies to 3 squared A of n minus 2. Of course, this formula only relies on the previous value. So what does A of n minus 2 look like? Well, we do the same thing. We have an A of n minus 2 here. Let's plug in A of n, where we replace all of the n's with n minus 2's. That looks something like this: 3 times A of n minus 2 minus 1, or just minus 3. Oops, minus 3. So this is what we're plugging in to A of n minus 2. So what do we get? We get 3 squared times 3 times A of n minus 3. That makes sense to everybody. And of course, this simplifies to 3 to the power of 3 times a of n minus 3. And at this point, we can kind of see a pattern emerging. And recursion is all about patterns. So every time we go down 1 in our iteration, we see the superscript of 3 increase by 1. We see the subscript of a decrease by 1. So we can kind of generalize a formula. We can go all the way up to n minus n. So a of n minus n. What does that look like? Well, we know that the formula seems to always depend on the value of the index previous in our recursion. So we can't go this far. The furthest we could go is a of n minus n plus 1, right? Because a of n minus n would be the first value we could give in our sequence, because a negative index is impossible. So what does that look like? That's just 3 to the power of n times 3 times, 3 to the power of n times a of n minus n, right? And of course, a of n minus n, what is that? Well, a of n minus n is 0, or a of 0. And we know what a of 0 is because we've been given it as part of the question. It's our initial condition. So this is just equal to 3 to the power of n times 2. And we're done. We've solved our recursion relation for a formula that can give us a value for any index in our sequence. We just plug in n for any index and we can get a value out of it. We also see that to be able to solve for that value, we have to incorporate a of 0 somewhere in our solution, right? That's why I was given. If we had gone too far and we had gone to a of n minus n, then this would have become a of n minus 1, which is a negative index, which is why we could not go that far. The furthest we could go was a of n minus 1 plus 1. And that allowed us to get a of n minus n somewhere in the formula, replace that with a of 0, and replace that again with what was given, 2, to get our final solution. We're given an initial condition, and we're given the recursion relation as well. So we have a of n. A of n is just n plus a of n minus 1. And what do? Well, we see that it only depends on the previous value in our sequence. So let's replace a of n minus 1 with a of n, where every n is replaced with n minus 1. So what does that look like? Well, we get n, nothing changes with n plus n minus 1 plus a of n minus 2. Right? Everybody can see that. We're just plugging a of n minus 1 plus n in for a of n minus 1. So we're replacing n minus 1 with n minus 2. That's over here. We're replacing n with n minus 1 right over here. This n is just a remnant from the previous formula in the iteration. And we can simplify this. Let's just say that this is n plus n minus 1 plus a of n minus 2. All right, so us kind of just doing some algebra to obtain this formula here. So we continue. What's the next iteration look like? If we plug a of n minus 1 plus n in for a of n minus 2, or that is to say we plug in a of n minus 3 plus n minus 2 in for a of n minus 2, what does that look like? Well, that looks like this. N plus n minus 1 plus n minus 2 plus a of n minus 3. Can everybody see that? Now, of course, this is the same as saying n plus n minus 1 plus n minus 2 plus a of n minus 3. Right, so we can just see this simplifies to this formula over here. And at this point, we can see a pattern emerging, right? Every time we iterate, we see this sequence in front increase, right? This summation sequence, n plus n minus 1 plus n minus 2. We can assume that as we get to a of n minus 3, this will just add on an n minus 3, and then n minus 4, n minus 5, plus n minus 6. And then at that point, we also increase the subscript of a of n minus 1. So let's just generalize up to a of n minus n. Okay, so we see that we have a sequence increasing, adding, and as we go, we add n minus 1 and keep recurring through that. So n becomes n plus n minus 1 plus n minus 2 plus n minus 3 plus n minus 4, all the way up to n minus 1. So we kind of have this summation sequence. And of course, at the very end there, we add a of n minus n. We can see that a of n minus n is just a of 0. And we have that as the initial condition, which is given. So what does this all simplify to? Well, this geometric sequence of sorts just simplifies to a times n plus 1 all over 2, right? And you can kind of have that memorized. That's just the truth. You know, that's what all that simplifies to, n times n plus 1 all over 2, plus, of course, 1. This 1 coming from that initial condition. And this again simplifies just to n squared plus n plus 2 all over 2, right? If you really wanted to, you know, simplify it even further, this would be your solution to our recursion relation. The next one, D. A of n is equal to 3 plus 2n plus a of n minus 1. We have a of n. We are given an initial condition, a of 0 is equal to 4. So let's work backwards and try to use it somehow in our solution. So a of n is equal to 3 plus 2n plus a of n minus 1. So all it depends on is the previous value in the iteration. So we have a of n minus 1, so let's just plug in a of n, replacing all of the n's with n minus 1's. So what does that look like? That's just 3 plus 2n plus, and of course, this a of n minus 1 is kind of expanded, and it becomes 3 plus 2 times n minus 1 plus a of n minus 2. Can everybody see that? And this is just simplifies to, so this step is us just simplifying this previous step. Okay, so from there, we have an a of n minus 2. So we just plug in a of n, replacing all of the n's with n minus 2. Okay, so it gets pretty confusing pretty quickly, but we see that this 2 times 3 plus 2n plus 2n minus 1, all of this is a remnant from the previous iteration, right? All of this matches here. While this segment over here is just a of n minus 2 expanded when plugging in what we've been given with a of n, replacing n's with n minus 2's. What does that kind of look like when you simplify it? So at this point, we can definitely see a pattern emerging, right? So if we just go on and on up to a of n minus n, we get, so we can see that we continue to increase our relation. We see a geometric sequence occurring, right? N times 3 plus 2n plus 2n minus 1 plus 2n minus 2 plus going on and on and on until we reach 2 times n minus 1. And of course, we have plus a of n minus n at the very end there. And so let's replace a of n minus n with 0, because we can do that. So this just simplifies to 3n plus 2 times n times n plus 1 all over 2 plus 4, right? N minus 1 is the geometric sequence. The times 2 is the times 2 in front right there. And this 3n is just what's given at the very front of our equation. Doesn't really match up with the geometric sequence. This plus 4 come from the initial condition, a of 0, which is very hard to look at, I understand. It's hurting my head right now, I assure you. But all of this just simplifies to n squared plus 4n plus 4. And that would be our solution to our recursion relation. G, a of n is equal to n times a of n minus 1, and our initial condition is 5. Okay, so we have what we've been given, and that's the kind of first step. We write down the original formula for our recursion relation, and we see it only depends on the previous value in our iteration, a of n minus 1. So let's replace a of n minus 1 with the initial given relation, all n's being replaced with n minus 1's. Of course, that will look like n minus 1 times a of n minus 1 minus 1, or just minus 2. So this formula is going to be replacing a of n minus 1. Whew. Okay, so what does that look like? That's equivalent to saying n times n minus 1 times a of n minus 2. Can we all see that? Okay, what comes next? Well, n times n minus 1 times n minus 2 times a of n minus 3. We continue. N times n minus 1 times n minus 2 times n minus 3 times a of n minus 4. And we can already see a pattern emerging, right? We just continue to multiply against n minus 3 every time. So, what is that going to look like? We get n times n minus 1 times n minus 2 times n minus 3, and we continue to multiply and multiply up into n minus n minus 1 times a of n minus n. Right? So we had some geometric sequence. It ends up with times n minus 1 times a of n minus n. Now this is just a of 0. So we see a pattern emerging. We also see that we continue to multiply the previous value minus 1. The previous value minus 1 times the previous value minus 1. Or, n minus 1, n minus 1, so on and so on. Now, do we know an operator that this can simplify to? Right, let's say n is 5. We had 5 times 4 times 3 times 2 times 1. What does that look like? Well, of course, that's a factorial. N factorial times a of 0, which is 5, 5 times n factorial is our final solution. Okay, everybody? So let's move on to a word problem. Suppose the number of bacteria in a colony triples every hour. A says, set up a recurrence relation for the number of bacteria after n hours have elapsed. So, we just want to set up a recurrence relation. We know a recurrence relation is defined as B of n, right? B of n being the number of bacteria, and n being the number of hours which have elapsed. And it's pretty easy. We see that it triples every hour, so it's 3 times the number of bacteria that were the previous iteration, the previous hour. So this is the same as saying 3 times B of n minus 1. And we're done. This equation here would define our recurrence relation. So we go on. If 100 bacteria are used to begin a new colony, how many bacteria will there be in the colony in 10 hours? Okay, well, we see that b of 0 is given as 100, and we want to go up to 10 hours. So, we begin with our equation, b of n is equal to 3 times b of n minus 1. What happens when we replace b of n minus 1 with b of n, replacing all the n's with n minus 1? It's kind of a mouthful, but it looks something like this. 3 squared times b of n minus 2, right? And where have we seen this before? This continues. 3 to the power of 3 times b of n minus 3. And we already see a pattern emerging. We've done this before. The same formula has arisen. So when we do this up to n number of iterations, and we try to get to b of n minus n, that's just 3 to the power of n times b of n minus n, right? And of course, that's just 3 to the power of n times b of 0. Right, so we're given that n is 10 and b of 0 is 100. So 3 to the power of 10 times 100, we plug in the values, and what does that look like? Well, me doing the math completely in my head, that would just become 5,904,900 bacteria, which will have developed in the colony after 10 hours. Okay, everybody, so we move on to our final problem. Factory makes cars at an increasing rate. In the first month, 1 car is made. In the second, 2 are made. And so on with n cars made in the nth month. So for month n cars are made. We set up a recursion relation for the number of cars produced in the first n months by this factory. Let's say C of n is the number of cars produced up to this point. Well, it's simply the number of cars produced up to the previous month's point, plus the number of cars produced at the nth month. So plus n. So then that would be our recurrence relation. How many cars are produced in the first year? Well, obviously the number of cars produced in the first year would be C12. To compute this, we need a recurrence relation and an initial condition, then plug n equal to 12. Alternatively, we could just compute the values, C of 1, C of 2, C of 3, up into C of 12. Let's set it up. Let's say that C of n is equal to n plus C of n minus 1. We say that this is just equal to C of n minus 1. We just take our recursion relation we've written, replace all of the n's with n minus 1's, and what does that look like? That looks like C of n minus 2 plus n minus 1. So we plug this in place of C of n minus 1. That's just n plus n minus 1 plus C of n minus 2. And of course, this is just can be simplified as n plus n minus 1 plus C of n minus 2. Right? We're seeing a similar pattern emerge from another previous problem we've done before. Whew. Okay, again we see a pattern emerging. We have a summation sequence here, n plus n minus 1 plus n minus 2. We can assume this pattern continues up into including n minus 1. So that's just, we skip a few steps of course, equal to n plus n minus 1 plus n minus 2 plus ... up to and including n minus 1 plus C of n minus n. Okay, we replace C of n minus n with C of 0. And when we have a summation sequence that matches this, right, we have n, we're continually adding n minus 1 and n minus 2 up until including of n minus 1. That's just equivalent to n times n plus 1 all over n, right? Kind of our best friend over here. This equation pops up a lot. Plus, what is C of 0? Well, C of 0 is the number of cars we have at the 0th month, which would be 0 cars made up to that point. So C of 0 is 0, so we have a plus 0 over there, and that is simply 2 squared, or n squared, plus n all over 2. Okay, so we've come up with a formula, and we are almost done with part B. Again, the question reads, how many cars are produced in the first year? Now, of course, n represents how many months have gone by in our formula. So if we just plug 12 in, we get 78. 78 cars were produced in the first year by this factory. Part C reads, find an explicit formula for the number of cars produced in the first n months by this factory. And, we already solved that by doing it the hard way, by doing B the hard way. So that's just n squared plus n all over 2. And those are our solutions, and we're done with the problem. Okay, everybody, I guess that wraps it up for recitation. I'll post more videos next time we have a global pandemic, right? Don't worry too much about the final, of course, because, it's a win-win whether you pass or fail. If you pass, you pass, but if you fail, then we get to hang out again for another semester.